Welcome to this explainer. Listen, if you've ever sat in a physics class, stared at a whiteboard covered in a million Greek letters, and felt just a rising sense of pure, unadulterated frustration, I want you to know right now you are absolutely not alone. It's incredibly common to feel overwhelmed by the subject. But today, we're going to completely flip the script on how you look at it.
Because, let's be honest, most of us first meet physics as this seemingly endless, intimidating list of formulas. F equals ma, v equals d over t, e equals 1/2 mv squared. You're told to memorize them, plug in the numbers, solve the problems, right? And very quickly, the whole thing just starts to feel like a dry, tedious exercise in simple shuffling. It feels way more like a catalog of random results to memorize rather than, a dynamic way of seeing the actual world around us. But here's the secret. Physics actually didn't begin as a giant pile of math equations.
So that really begs the question, what is physics actually for? Well, it actually began as a desperate, passionate human attempt to answer incredibly concrete mysteries. Why do things fall? Why do planets wander across the night sky? Why does a cart eventually roll to a stop, but the moon just keeps on going night after night? Every single formula you've ever been asked to memorize was actually invented to solve a specific, deeply human problem.
Which brings us to Section 1, Aristotle's two worlds.
Okay, let's dive right into this by traveling back in time a bit. Imagine standing under a perfectly clear night sky thousands of years ago. This is way before telescopes, before textbooks, before the word physics even existed. The stark contrast our ancestors saw was just incredible. They looked around at the Earth, and motion down here looked incredibly messy and temporary. You throw a stone, it goes up, slows down, falls. A rolling cart rattles along and then just stops. Smoke curls up and disappears into thin air. Basically, things move and then they die out. But when they looked up at the heavens, motion up there looked perfectly clean and stunningly permanent. The sun traces the exact same path every single day. The stars rotate together in lockstep. Even the wandering planets move in these long, graceful, repeating cycles. So the first great problem of early science was basically, how can one single world produce two entirely different kinds of motion?
Well, for ancient thinkers like Aristotle, the answer was pretty simple. They don't. Aristotle actually believed there was one set of rules for the sky and a totally different set of rules for the ground. He explained motion in terms of purposes and tendencies. So heavy objects, like rocks, naturally seek the earth. Light objects, like fire, naturally seek the heavens and rise. And the heavens themselves, they naturally move in perfect eternal circles. It was essentially a physics of what does this object normally want to do. And honestly, for centuries, this picture made perfect sense. I mean, it fit exactly what people saw with their own two eyes.
But eventually, things shift. Section 2, Galileo's ideal world.
Yeah, eventually that perfect ancient picture began to crack. Enter Galileo. Now, he didn't just wake up one morning and decide to invent classical mechanics. He just started asking these really specific, nagging questions. For instance, according to the old logic, a heavy rock should fall way faster than a light rock, right? Because it has a stronger tendency to seek the earth. But Galileo asked, why is it that if I drop a heavy ball and a light ball from a height at the exact same time, they hit the ground at almost the exact same moment? Or why does a ball rolling on a super smooth surface keep going so much further than one on a rough surface?
So the really crucial point here is how Galileo decided to actually attack this problem. He realized that our everyday experience is cluttered. It's just full of friction, air resistance, and imperfections that hide the underlying truth. To find the real rules, he had to do something pretty radical for the time. He had to use his imagination. He decided to strip away the complications we see every day. He imagined a simpler, ideal situation, objects sliding without any friction whatsoever, or falling in a complete vacuum without any air resistance. He asked, what rule would hold true there?
With this, we were undergoing one of the most massive shifts in human thought. Think about it. We moved from Aristotle 2,000 years ago, asking how do things normally move based on their inner purpose, to Galileo 400 years ago, asking what precise underlying rules govern motion if we just remove the earthly mess. And that shift perfectly set the stage for Isaac Newton 350 years ago, who took this entirely new way of thinking and just blew the doors off the universe.
Which leads us to Section 3, Newton's universal law.
By the time Newton arrived on the scene, the world had definitely changed. Astronomers like Copernicus and Kepler had already proven that the Earth was not, in fact, the center of the universe. The Earth was just another planet, spinning through space, and Kepler had even shown the planets move in precise mathematical ellipses. Now, this presented Newton with an incredibly ambitious, almost terrifyingly grand problem. See, he wasn't about solving textbook questions. His problem was this. If the Earth is actually in the heavens,
Can one and the exact same set of laws explain both an apple falling from a tree on Earth and the moon orbiting in the night sky? Could he finally unite Aristotle's two broken worlds? To solve this seemingly impossible puzzle, Newton literally had to invent entirely new tools. First, he needed a clear mathematical way to describe exactly how a position changes over time, so, he just helped invent calculus. No big deal, right? Second, he needed a way to connect those changes in motion to an actual cause, so he formalized the entire concept of force. And finally, he needed a mathematical link that could calculate an invisible pull acting across millions of miles of empty space, and that, of course, was his theory of gravity.
And this brilliantly illustrates the true beauty of Newton's work. Those laws of motion and universal gravitation that you see taking up hundreds of pages in your textbooks, they aren't just arbitrary rules designed to make you calculate the speed of a block sliding down an inclined plane. Not at all. They are the specific, majestic language Newton created to make one profoundly simple statement. The sky and the ground obey the exact same physics.
Bringing us to our final part, Section 4, the real physics.
So this brings us to how you can completely change your experience as you learn this subject moving forward. The next time you're looking at your notes, I want you to remember this framework. When you learn about velocity and acceleration, remember they aren't just random variables. They are the direct answers to Galileo's struggle to describe motion precisely in an ideal world. When you're sweating over Newton's laws of motion, remember you're using the exact framework designed to unify falling apples and orbiting moons. And when you finally get to the concept of energy, know that it was invented as a response to the frustrating problem of trying to track what stays the same when forces do incredibly complicated work. The formulas? They're really just the solutions to these epic historical mysteries.
So, if we step back for a second, we get a much better, much more inspiring definition of what we are actually doing here. Physics isn't just a catalog of results. It is a way of turning deep human questions about the world into clear, testable statements. Honestly, it's our greatest attempt to understand the stage we are standing on.
And that leaves us with a totally different way to approach your studies. The next time you sit down in class and the teacher writes a long, terrifying equation on the board, I really don't want you to just ask, how do I plug the numbers into this? Instead, I want you to ask yourself, what deep, ancient mystery does this formula actually solve? Keep that question in mind, and you won't just be memorizing math, you'll be uncovering the secrets of the universe.